in regional policy and research. She's particularly interested in topics related to geographic data science, data visualization, spatial statistics, open data, and reproducible research. In her free time, she also enjoys working on cartography and design projects. And then another fun thing is she is a very active Our Lady, member of Our Ladies, I guess, however you want to put it, Our Lady. So that's cool. And also, if you're interested in joining Our Ladies, you can talk to one of us. So thanks for coming to the last talk, and here we go.
Yeah. Hi, everyone. My name is Katie. So a little about my background. I think of myself as primarily a geographer, but I also use data science to do that sort of geography work. And so a lot of what I think about is how to translate sort of geographic theory into data science and into sort of actionable things that we can do to sort of measure the way that we think about space and how people distribute themselves in space. So I was initially trained sort of using desktop GIS software. So if you've used ArcGIS, QGIS, those sorts of things, that's where I first sort of learned anything that relates to data science. And so that's a lot of how I think about the work that I do. But I want to sort of frame geographic data science sort of contrasting with desktop GIS. And I like this framing a lot. It's very interdisciplinary with geography, computing, and statistics, so you get a lot more of that sort of performance and speed that you can get with computing and some of the computing theory that you're missing in desktop GIS. There's more of a code-based workflow, which makes it easier to collaborate, easier to change, easier to update your work. And it also is maximally reproducible as opposed to sort of point and click software, which is one of the highlights of using software like R and Python. It also is, desktop GIS is largely sort of proprietary software still, which goes into sort of the reproducibility argument as well. So geographic data is a very large category. I'm going to talk about a very small sliver today, but I'm happy to answer questions about larger themes in geographic data and data science. So the first sort of type of geographic data that we deal with is raster data. So if you think of sort of aerial imagery, if you go hiking and have an elevation map of your route, that is raster data. So in raster data, we divide up space into sort of grid units. The size depends on your data source, but often they'll be like 5 kilometer by 5 kilometer units. And you have some sort of value in that unit. So if you were measuring elevation, each of those sort of raster grid units would have like an average elevation within that area. I don't use raster data a whole lot, but it's really useful for a lot of things. A lot of ecologists use a lot of raster data and things like that. So what I use more is vector data. Vector data, you can think of things like census data, points on a map, roads, sort of discrete divisions of space, and sort of discrete objects in space. The three main types of vector data, and really the types of vector data are points, lines, and polygons. And if you want to get into sort of data types, there are some more specifics as you get into things, but the three broad categories being points, lines, and polygons. So now that we sort of have a brief overview of what we're thinking of when we think of data that is geographic, I want to talk about really just one of the quirks of working with geographic data. And if it works, I have a short video. So projections and coordinate reference systems are something that's very unique to geographic data and the way that we use geographic data. So the Earth is a geoid or a sphere, but our maps are 2D, and we have to think about how we translate those 3D objects onto a 2D space. So if you think about peeling an orange and trying to lay that peel flat, you can't. There has to be some distortion there. And so whenever we make a map, there's going to be some level of distortion. You can see these 4 maps, none of which is correct, of the US, and they all look different. To me, some look a lot nicer than others. So different maps are good for different purposes. The Mercator projection is one of the most common. It's really useful if you're going to sail across the ocean. Points like the straight line distance between points on that map is going to be correct. Whereas something like an equal area map might be better for doing analysis by area. It maintains the area of a unit, but not necessarily the distance between them. So if anyone is a fan of the West Wing, I have a short video I want to show about projections. Oh no. Okay.
Brian?
You are.
Josh, this is Dr. Gallo, and Mike, who's Marinette.
Yes.
Should we begin?
Yes. Plain and simple, we'd like President Bartlett to aggressively support legislation that would make it mandatory for every public school in America to teach geography using the Peters projection map instead of the traditional Mercator.
Give me $200 and it's done.
Really?
No. Why are we changing maps?
Because CJ, the Mercator projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World.
Really?
The German cartographer Mercator originally designed this map in 1569 as a navigational tool for European sailors. The map enlarges areas at the poles to create straight lines of constant bearing or geographic direction.
So it makes it easier to cross an ocean.
But it distorts the relative size of nations and continents.
Are you saying the map is wrong?
Oh dear, yes. Now look at Greenland.
Okay.
Now look at Africa.
Okay.
The two land masses appear to be roughly the same size.
Yes.
It would blow your mind if I told you that Africa is in reality 14 times larger.
Yes.
Here we have Europe drawn considerably larger than South America. When it's 6.9 million square miles, South America is almost double the size of Europe's 3.8 million.
Alaska appears 3 times as large as Mexico, and Mexico is larger by 0.1 million square miles.
Germany appears in the middle of the map and it's in the northernmost quarter of the Earth.
Wait. Relative size is one thing, but you're telling me that Germany isn't where we think it is?
I think it's where you think it is.
Where is it?
I'm glad you asked. The Peters projection.
It has fidelity of axis.
Fidelity of position.
East-west lines are parallel and intersect north-south axes at right angles.
What the hell is that?
It's where you've been living this whole time. Should we?
All right, so that is all I will show of that. But they do it in a much more funny way than I would, so I figured that better to watch that video. So sort of the point of that is that projections matter, but they're kind of weird. And there are thousands of different projections you can choose from, but for something around the size of a state or smaller, which is the type of analysis I'm usually doing, there are 2 good systems, state plane zones and universal transverse Mercator or UTM zones. And so as you're starting to work with geographic data, these are not always the best, but there are 2 ones that you know are pretty good. So essentially how you use them, you would look to see like what state plane zone your study area is in or is mostly in, and then sort of choose from there. So for example, I believe that the Twin Cities are in Minnesota South. Similar for Universal Transverse Mercator, they're just more up and down, and these are global, whereas state plane is only for the US. And Minnesota is in UTM 15 North. And you sort of start to learn these things as you work with this data. Many states and cities also have recommended projections, and so it's worth doing that background research before you do your analysis. So the sort of application I want to talk about today is honeybee permits in Minneapolis. Minneapolis Open Data has a point data file of all the registered residential honeybee permits. So I'll talk about how to read in data, reprojecting data, making basic maps with ggplot, spatial joining, what a spatial neighborhood is in terms of analysis, how to look at and then measure whether or not things are clustered, and then the modifiable aerial unit problem, which is sort of a logical fallacy that we see in geography. So first, reading in spatial data. So the most common form of spatial data is the shapefile, which is actually a collection of like between 4 and 6 different smaller files. For example, the PRJ file contains the information about your projection, and the other files contain different parts of your spatial data. So if you lose one part, it can mess up your data, and that's really, really frustrating. There are other forms of data like GeoJSON and GeoPackage, which are nicer. They have just one file, but it's been slower to catch on. So much of what we do is based off of shapefiles. It's really hard to change that. But when you read it in, it's also tricky because it only looks like you're reading in the .shp file, even though it's reading information from all the rest. What's really nice is that a lot of open data portals have API endpoints. I try to use API endpoints when I can. It avoids that file management issue, and it's just easier when I'm teaching people or when other people are running my file. So I like to use API endpoints when possible. So now we talked about projections, but from a more technical standpoint, so we can look, I'm using the SF package here in R. We can look at the coordinate reference system of our honeybees data. So when we look at this, it looks kind of abstract. But when I look at this, I notice the proj equals long lat. So it's geographic, not projected, and the only thing you need to know about that is that you don't want geographic, you want projected. So you can change it to UTM 15 north. This happens to be the code for that. So SF objects have a plot function built in. It doesn't look super nice, but it's great for just getting a quick look at your data. But SF objects also work really nicely with ggplot. And so you can make this sort of basic map that's really more similar to a scatter plot in a lot of ways. And you can also add contextual data with the nice sort of layering logic of ggplot. So here I've layered on the neighborhood shapefile for Minneapolis. And so when I'm looking at this map as a geographer, I'm sort of asking myself questions about the way that things are distributed in space. And one of the most common questions is sort of, are these points clustered in space? And so as a data scientist, I also want a way to quantify that and put some sort of confidence on that. So we can use what's called a spatial join. So one way to think about clustering is, are these permits clustered by neighborhood in Minneapolis? That might be a policy question that we might ask. So we can do something called a spatial join, where essentially we overlay those points onto some other shapefile. In this case, it's those neighborhoods. And what we're doing really is counting how many points there are in each neighborhood. And you can do that really nicely with dplyr syntax. You can do it with data table syntax. You can do it with base R syntax as well. But this, I think, is the most concise way to do it. And so we can see that on average, there are about 1.5 permits per neighborhood. But another question we might ask is this equally likely everywhere in the city? Are we equally likely to see 1.5 permits? Or are there certain neighborhoods where you're more likely to see more permits than others? So we can look at this map again, now mapped by neighborhood with counts of permits. Again, this is just made with ggplot. And we start to look, so raise your hand if you think this looks clustered. Okay, raise your hand if you think it looks pretty random. Okay, who thinks it looks dispersed? And who knows the difference between random and dispersed? Okay, so in geography, the first law of geography is that everything is related to everything else, but near things are more related than distant things. And that's really what we're trying to quantify with clustering, is like how related are near things compared to distant things. So we need to think about what does it mean to be near something. So two common ways to do that are Queen's case and Rook's case contiguity, both coming from chess moves. So Queen's case is different in that it includes corner cases, so it's more inclusive. So this is the code to sort of create that weights matrix. It's a 1-0 matrix. Are you a neighbor or are you not? Zeros along the diagonal, I believe. So, and then you can create this crazy plot. It doesn't really tell you anything, but we know that on average, each of the neighborhoods in Minneapolis has 5.6. Queen's case neighbor, with just looking at the map, that makes sense. A lot of the neighborhoods are pretty like square. So when we talk about clustering, dispersed means that you're more likely to be near something that is dislike you. This is pretty rare to see in space. It's far less likely than clustering. You see it more in biology, where sometimes like root structures make it such that other similar plants can't grow near them. And so that, if you see a checkerboard pattern, that is dispersion. randomness is that thing in the middle where it's like you can see some like small pockets of clusters, but there doesn't look to be any global pattern. And then finally, all the way in the end of the spectrum, we see clustering where there's that clear sort of division of values. So that's what we're looking to quantify. So how we do it is with a statistic called Moran's I. It's basically two-dimensional correlation coefficient. So you can plot on the y-axis, this case, the example is income, the income of your neighbor and your income. If you see a positive slope, that's clustering, a negative slope, that's dispersion, and zero slope, that would be random. And that's how you can sort of see it on a graph. So it's really easy to run this in R, and I really like using the Monte Carlo approach to significance. So what that does is it randomly generates 10,000 or whatever you give it, different random distributions on your space. And then it looks at where your distribution falls in that simulated distribution to give you a p-value. That's nice because not all sort of like geographic structures look the same when they're random. So it's nice you're just evaluating it within the context of your data. So here we can plot. It doesn't look great because it's whole numbers, but bear with me. So to me, this line doesn't really look, and on my computer, I can see that the standard error bars are like pretty wide. To me, this doesn't really seem to follow any specific pattern. Some of that is just because we don't have a ton of neighborhoods to work with. And we see that our statistic is like fairly close to zero in the grand scheme of things, and our p-value is also not significant. So we would say that our permits are distributed spatially randomly across neighborhoods. When we look back at this map, knowing what we do about dispersion, randomness, and clustering now, that kind of makes sense. It looks closer to that random pattern, right? Like we see pockets of clustering, but we don't see a clear division. But that brings us into the modifiable areal unit problem now. So if we look at these three images, they all have the same underlying distribution of points, right? But when we aggregate it to different levels of geography, the maps look really different. And so would our permits look different if we aggregate it to something other than neighborhoods? So if we aggregate it by census block groups, we see a really different pattern. To me, this looks more clustered. You see like lines of permits that are all sort of adjacent to each other. And so to me, it looks more clustered. We can run our Moran's I again, and we see the statistic is 0.2, so not super clustered, but it is clustered in a p-value that's essentially 0. It was the most extreme of our simulated distribution because the observed rank is 10,000. So now we see a really different picture. This might lead us to believe that permits are clustered in Minneapolis. But before we found that it wasn't. And so this example is kind of like not super impactful, but what could be some consequences of this? So a lot of my research is in gerrymandering. I do a lot of computational methods in gerrymandering. Also happy to talk about that. And sort of the crux of the problem with gerrymandering and political districting is that how you carve up space matters. So you might have the same underlying distribution of voters. Think of that as our points of honeybee permits. But how you divide up into districts can really change what that map looks like, right? And so a lot of gerrymandering work has been figuring out how to divide it up in a fair way. And so this is, in geography, the modifiable areal unit problem. So this is a really important thing to keep in mind. My advice to people is when you're doing an analysis at some areal unit, think about how you want to communicate your results and what level your results are important at, and that should be how you aggregate your points or your data or whatever else. And also you can do some robustness checks and just aggregate your data to different spatial units and see if you're getting similar results at each one. If you're not, that might be something you can look into. So thank you for listening, and I'm happy to answer any questions you might have. And I can't see everyone, so feel free to shout out.
I do a little bit of spatial work in R. And then I find myself taking the output from R and loading it into a desktop GIS to visually inspect it a little more closely, and it always feels a little funky. I'm just wondering, do you use that same flow, or is that just a trap?
A little. I've been trying to force myself to not and to like just use R. And so like on my work computer now, I don't have desktop GIS because then I can't use it. And so it like really forces me to use R, but like on my personal laptop I do. And so yeah, I do a fair bit of like translating back and forth. There are some packages to connect to QGIS and things like that, but it's more to use the algorithms that are available there than to like connect your data. And so, yeah, I'll do a fair bit of like, I'll save my like desktop GIS project in the same folder. And so then it's easy to like reload the data. I haven't found a good workflow for that for sure. Like getting more confident with things like Leaflet, MapView, those where it's sort of like easier to see your data and like click around a little bit. But yeah, that's still something I'm like trying to integrate into my workflow. Yeah, design is still difficult in R, just because you can't like move the text just a little bit. It takes a lot more. So I think that's still something that like I work on a lot. Yeah.
You mentioned you do like research on gerrymandering. Can you like talk a little bit about that and like how you got into that?
Yeah, Christina, I can talk about that. Okay, so yeah, my research is primarily like before you get to the gerrymandering step. So it's like the way less exciting part of it, but in my opinion, very important. So in a lot of areas, precinct shapefiles are not available. So yes, I see all your faces. It's crazy, I know. And so last summer, I started a project with a group. So we specialize in Ohio data where like almost none of it is available. And to do any sort of gerrymandering analysis, you need precinct level data, not county level data. So we called all 88 counties in Ohio and talked to some nice people and some people who weren't so nice. And when we said we were from a voting rights group, a few people hung up on us, which was like, okay, interesting. And so we got shapefiles from as many as we could, about 50. And then we had about 30 people give us PDF maps or paper maps. So we digitized like 450 images of maps. A lot of the maps came to us like in parts. Our biggest one was about 10 feet by 10 feet. So we had to use the architecture school scanners at MIT. So we made some good friends there. And then, so that was like a lot of the project. And then my part, like the computational part. So there are 8 counties that never responded or had no data. I actually don't think that they were kidding when they said they don't have maps. I wouldn't be surprised. But we still need to include them in our precinct shapefile. So the voter file in Ohio is public information. So I have people's addresses and I know what precinct that they vote in. So I can hit the Census Bureau API with their address. It gives me what census block someone lives in, which is a small enough geography for me. And then you can, with that, you get about 60% coverage of census blocks. And then you can write an algorithm of like, what's the most likely precinct for all the census blocks that don't have a voter in them. And then create a shapefile from that. And yeah, that's my research, is figuring out how to build precinct data when it doesn't exist. So other people have done it, but it's like thousands of dollars, but I'm free. So yeah, so we do all of our work open source. And yeah, we work with like the ACLU and a few other civil rights groups to provide them with data. Yeah.
Wait, so doesn't the Ohio state government have a list of what precincts are in what district?
No, so so they have like lists of people and like what precinct that person is. So precincts are done at the county level, not at the state level. So the state has nothing to do largely with how precincts and voting is administered. So that's a big problem with funding. So like rural counties don't have funds to update their voting systems, and probably could benefit from a state system. I have a lot of thoughts about how funding works for voting, but yeah, so like the state doesn't have anything to do with it. And the counties, I mean, these are like rural counties. The maps we were getting were from the 40s, pre-highways, and really difficult to navigate on OpenStreetMap. But like that's the maps they're working with. Like this is, so like we called one county and like their precinct guy, like he moonlights as a precinct guy, but he's like their soil and water conservation expert. But he just like thinks precincts are interesting, and he does all of their voting stuff in the entire county. And so it's just like very overworked people with zero resources. And so I hold no hostility towards them. Yeah.
I have a follow-up.
Yeah.
Hit the floor, but well, so then every 10 years when people sit down and draw the district, do they not save that data? It seems like they're drawing on a map then.
So that's data that costs tens of thousands of dollars. So like the people, the consultants who draw the districts have that data, but they do not share it because it takes so long to compile it.
Yeah.
If I were smarter, maybe I would charge for it, but yeah, no, it's a huge amount of work to keep it updated. So like I can't constantly update it. So my data falls out of date pretty quickly, and I rely on people who help me to keep it up to date. But we basically say this was up to date as of this date. Yes.
So I've only been working in car for a few years, but the impression I get as I've been working with spatial art packages, they're a lot like newer and a lot more organized than a lot of the other packages and programs are. And I'm just wondering, like, how is there like an organized effort towards developing art spatial?
Yeah. So yeah, there are like lots of different algorithms and lots of different packages. But there's an effort to like put a lot of the time, energy, funding, all of that into a package called SF, which links to sort of like PostGIS library. So it's nice because if you work in like other sort of spatial database world, the names are pretty similar, which is nice. So yeah, a lot of that development work has gone into SF, which has really improved over the past few years, and it's become sort of like the centralized library for spatial analysis. But so like if you notice here, I have to convert it back to a spatial polygons object because like those sort of like neighborhood like structure functions are still in the SPDEP package, but I think over time the effort is to like move them. I would put in a vote for the geocomputation with our book. That's a really nice like book. It's online, it's free, and the people who wrote it are like definitely the experts on geographic data science and R, and they come from a variety of different backgrounds: ecology, marketing, and transportation. And so the applications are really diverse, which is really nice and kind of rare to find in a geography book. And so that is sort of a way to like write out like here are all these things that you can do and how to do them. But yeah, I would say the SF package is sort of where the work is going, and different packages built off of SF. Sometimes I find myself just sort of like rewriting the algorithms that you can do in SPDP that are like quick to recode, so I don't have to like move my data back and forth, but that requires like knowing the algorithm that goes into it. So I don't necessarily recommend that as like a good workaround. Also, I shouldn't be doing that. So, but yeah, other questions? Yeah.
Occasionally there's entities that will put up multiple different types of vector files, big files, DODs. Can you say a little bit about the strengths and weaknesses of file types?
Yeah. So my least favorite is the Esri file geodatabase. My least favorite because you can only open it in Esri products, which are proprietary. Most people won't put up only a file geodatabase because they know that, but it's an easier way to store files in an organization that's built around Esri, which most big organizations that use GIS are. The shapefile's strengths are that it's ubiquitous. Anyone who works with geographic data has seen a shapefile and they know what to do with it for the most part. But the weakness is that when you try to make it open and make it easy for other people to do spatial analysis, like so often people come to me and they're like, oh, my shapefile's not working, but it's because they deleted everything except the .shp file because they figured it wasn't important because no one told them it was. There's no like disclaimer on the site, like don't delete these files. So they'll have like no attributes, no projection, nothing. So it's good because it's ubiquitous, it's easy to troubleshoot, it's easy to find help, but it's difficult because there's a lot of like implied knowledge when people use it. GeoJSON is good. I don't use GeoJSON a whole lot, and so I admittedly don't know like the strengths and weaknesses so much of that. But geo packages are nice. Also, that's what I use primarily. You can have column names that are as long as you want, which is not true with ArcGIS. It'll just cut off your column names and won't tell you, which is really hard for updating metadata. And so those are sort of like SQL databases. So if people don't know how like the database structure works, so like there might be multiple layers in your geo package, but if people don't really know what that means, then it's hard to communicate, and only like more recent versions of Desktop GIS support GeoPackage, so it's newer. Those are sort of the main ones you'll see. Trying to think. Yeah, those are sort of the big ones. There are others that like pop up, but I would say it's like you will do yourself well to learn how to use shapefiles well, because that's like you can get away with only ever touching shapefiles for the most part, and as long as you keep all the files. I like to just zip them up and keep a copy there in case I accidentally delete something, because I do that all the time. Yeah.
All right, thank you.
Yeah.
So everyone head down to the main room really quickly. Lindsay Dietz is going to do a drawing. There's some